Hello, welcome to, in specs I'm reacting to, time dilation visualized by the overview effect.
Project Hail Mary, but the movie glosses over what I love Project Hail Mary, but the movie glosses over what I love about Andy Weir's novels, and that's the science. I guess the general public is not into math and science, but I am, and I think fans of this channel are too, so let's do the math and nerd out even harder than the novel does on relativity, mass ratios, and the astrophage infection rate.
So going in depth.
The movie mentions briefly that it takes him 4 years to get to Tau Ceti, but Tau Ceti is 12 light years away. So if you can't travel faster than the speed of light, how can you get there in 4? Well, that's where time dilation comes in. We can't travel faster than the speed of light, but something weird happens the closer you get to it. Time.
I actually kind of know what happens when you get close to the speed of light. Basically, when you approach the speed of light, I'm talking like 98% of the speed of light. You can't go 100, but 99% of the speed of light, time kind of just slows down. Because you're going so fast that the concept of time literally cannot keep up. Because time travels at the speed of light. So theoretically, if you travel at 100% of the speed of light to someone living on Earth, to someone living on Earth, you are traveling an infinite amount of time, but for you, that. Again. Want to hear it again? I think my mic can't pick it up. Hey, there we go. Anyways, that is how fast time goes, but for you, it's way faster than even me snapping.
Time slows down. And if you keep accelerating, time keeps slowing down.
Yeah.
Constant acceleration is like the eighth wonder of the world. If you can keep it up, it's like compounding interest. Extremely far away things become closer and closer because of this time dilation, which begs the question to me, how long would it take to get...
The reason for that is because of how time as a concept works. It's space-time. Time is... There can be an argument that it is a particle. But that would be lying. It's a particle and a wave. Like gravity. Well, no. Hold on, I gotta think. As far as we know, gravity is a wave. And so is time. But time is also a particle. But it's also not a particle. If that makes any sense. So, the faster you go, gravity also slows down. Gravity and time squeeze together. And you end up traveling really, really fast. In a very short amount of time, because I think this video will explain it.
To get to Betelgeuse or the edge of our galaxy or the nearest neighbor galaxies? The answer is that we can travel anywhere in the universe within a human lifetime. Let's see it in action. Tau Ceti is 11.9 light years actually below us in relation to the galactic plane. But first, before we get to Tau Ceti, let's start with our closest neighbor. Let's start with Alpha Centauri and see what a hypothetical trip from Earth to Alpha Centauri would be like on the Hail Mary. This orange tube is not a wormhole. It's a representation of how fast time is going for our ship relative to Earth. We start the trip accelerating at 1.5 Gs. And we get up to relativistic speeds extremely quickly. After only 5 months of accelerating, we're already going more than half of the speed of light. And while 5 months have passed for us on the ship, time has already slowed down, and 6 months have passed on Earth. By the midpoint, we're traveling 97% of the speed of light, and 1.5 years have passed on the ship, but more than 2.5 have passed on Earth. If we want to come to a stop at Alpha Centauri, it's here where we have to flip around and burn to slow down, and our time dilation will start going back to normal as we slow down to normal speeds.
So basically, time slows down as you speed up. And then, because space is a thing and you cannot slow down on a dime like you can on Earth, gotta turn around, burn the engines, and then time starts speeding up I hate using these terms like speed up and slow down because that's not really what's happening. It's all relative.
But if we don't slow down, if we keep accelerating, time keeps getting slower. And that's the key. As we keep accelerating, our velocity tapers off because we can never get past the speed of light. It's asymptotic. We just keep adding nines to our 99.9 whatever of the speed of light. But the time dilation doesn't taper off. It's not bounded. The more we keep accelerating, the more time slows down. From the ship's perspective, it's exponential. Every additional year of acceleration, the time dilation roughly doubles. If we compare the trip to Alpha Centauri to the trip to Tau Ceti, as we keep accelerating, our velocity tapers off because we can never get past the speed of light. It's asymptotic. We just keep adding nines to our 99.9 whatever of the speed of light. But the time dilation doesn't taper off. It's not bounded. The more we keep accelerating, the more time slows down. From the ship's perspective, it's exponential. Every additional year of acceleration, the time dilation roughly doubles. If we compare the trip to Alpha Centauri to the trip to Tau Ceti, we can see this in action.
So basically, my brain's turning, bro. As far as I understand, the time slows down as you go faster and faster and faster, but since you cannot break the light barrier. What the fuck? Oh, I understand it now! It's because of... Hold on, I gotta pull out a chart. So basically this is a logarithm. Basically, how a logarithm works is you speed up really, really fast if we're going with a light thing. But, wait, no, this is 1c. Yeah, close enough. You cannot break 1c. A c is 1 light speed. Or it's about 300 kilometers every second. I don't know what that is in Imperial. But the time goes, fucking burr! Like, notice how it takes up, notice how it goes really, really slow at first, but once you pick up, you pick up. It goes brrr. That's basically what's happening with time. Time is an exponential. Basically, it's, it picks up really, this is exponential. It's to the power of x. This is basically what's happening with time. Log x. And this is basically what's happening with... This is time. This is how fast you're going. Except this is like way, way bigger. But you get the point.
The trip to Tau Ceti only takes about 1 year longer than the trip to Alpha Centauri, even though it's 3 times farther away. Rocky's trip from 40 Eridani took about the same too, because they're about the same distance from Tau Ceti than we are. They're about 10 light years. So the time dilation is pretty much the same if they took the same flip and burn profile, which they didn't. But to really see the power of this, we need to go much further. Betelgeuse is about 500 light years away. And with the same level of acceleration, the trip would only take 8.5 years. At the midpoint, we will reach 99.999% of the speed of light. I've scaled up the travel lines, but as often the case with cosmological distances, things are getting hard to see. To really understand the exponential nature of this, we have to change the way we're looking at this. We've got to move the stars around here. Let's compress everything based on how long it takes to travel to them. In order to illustrate that, let's add in some more stars, like the Pleiades cluster, which is a famous star cluster slightly closer than Betelgeuse, and the Orion Nebula, which is 1,000 light years further than Betelgeuse. And when we engage our time dilation, this is what happens.
I think that to Pleiades, it will take 9 years. And to the Orion Nebula, it can 10 years.
Remember, the farther away an object is, the more time dilation affects it. So the Pleiades and Betelgeuse are only slightly further than Tau Ceti and Eridani, and the Orion Nebula, which was 1,000 light years further, is now just slightly farther than Betelgeuse. Betelgeuse took 8.5 years to get to, and the Orion Nebula only takes 9.5. And you can kind of now see how it's getting squished up around the edge.
I was right. Huh.
And that's the same thing that's going to happen for the rest of the stars in our galaxy. Our entire galaxy becomes a squished shell right on the edge of our doorstep.
That's trippy, bro.
Other galaxies too get pushed.
Maybe when I take too many mushrooms. Yeah. Chat, don't actually take mushrooms.
Pushed right to the edge. The Large Magellanic Cloud, which is 160,000 light years away, takes 16 years. Andromeda, our closest large galaxy, which is normally 2.5 million light years away, takes just under 20 years to get to. The Virgo cluster, a cluster of a couple thousand galaxies, which is 54 million light years away, would take just 23 years and 7 months. And finally,
That's
the edge
trippy.
of the observable universe, 46.5 billion light years away, would take just 32 years and 3 months. At which point we will be traveling 99.99999999999999999 21 nines. The speed of light. And 46.5 billion years would have passed on Earth because we're basically going the speed of light. This would require a lot of energy. Actually, in this example, it would require a lot of matter because that's what we're doing. That's what astrophage is doing. It's converting matter into energy. Astrophage is like a little E equals MC squared bioengine. So how much matter do we need for this trip to the edge of the universe?
A lot.
About 500 sextillion tons, which is the mass of 87 Earths. And this starts asking the question, how much mass is too much? Because we're already idealizing a lot of things here. In modern rocket engineering, a mass ratio of 20:1 is considered realistic. That means the fuel weighs 20 times more than the ship. And in fact, that's exactly what the mass ratio of the Project Hail Mary was in the novel. The ship needed 2 million kilograms of astrophage to reach Tau Ceti in 4 years, and the ship weighed 100,000 kilograms, 20:1. Problem is, that was a mistake by Andy Weir. 2 million kilograms is what was needed if it was a flyby. To stop at the destination, you need to square that number. So what it really needed was 400 million kilograms. I reached out to Andy Weir and he responded and confirmed this, which would mean a mass ratio of 400:1, which is a little unreasonable.
Sweet
but we do have an option to
liberty.
save some fuel. We don't need to accelerate for the whole period. And that's what Andy Weir says he changed. He said he added a coast phase. Okay, so let's do the math. Using the same specs from the book, 1.5 Gs of acceleration, if we coast for 85% of the time, that is, we accelerate for about 1 light year, coast for 10, and then decelerate for 1, we'll get there in 6 years and 8 months. Confusing to me, in the movie they didn't fix this. There's a point at which, at the end, the computer says it's going to take 4 years, 2 months, and 11 days, which is almost exactly a 50% coast phase. So that seems intentional to me. Like maybe that was Andy Weir's fix to do a 50% coast phase. But with the 50% coast phase, the mass ratio becomes 124 to 1, which would mean the ship would have had to have weighed 16 tons dry or used more astrophage. And in the movie, they say it still uses 2 million kilograms of astrophage. But honestly, there are so many assumptions we're making here that 124 to 1, maybe that's plausible in this universe holding astrophage. You can play around yourself with these numbers on my website. This is a calculator on my website. Either way, I'm still inspired that it's still physically possible to reach other galaxies within the known laws of physics. Because there could be other methods of generating insane amounts of energy in the far future, like a Kugelblitz drive or something else crazy. And we could still get there without wormholes or breaking physics. While I'm in the mode of being an armchair physicist, there is one other flaw in Project Hail Mary that I thought was interesting. In the story, Tau Ceti is the only star nearby Earth which is not dimming due to astrophage infection. Canonically in the novel, as they're tracing back where it came from, they say that the sun was infected by WISE 08550714, which was infected by Sirius, which was infected by Epsilon Eridani. They also say that WISE
Wait, so hold on, astrophage, the fuel, that's what? It's an infection?
Infected Wolf 359, the Land 21185, and Ross 128. From this, they deduced that the range at which astrophage can survive interstellar distances is 8 light years, and thus the range that it can infect other stars is 8 light years. Problem is, in real life, WISE is 11 light years from Sirius, so that's a no-go. The shortest distance from Tau Ceti to Sol in less than 8 light-year hops would have been Tau Ceti to LaSalle 9352, LaSalle 8760, Ross 154, Barnard's star, and then Sol. I feel like I'm playing Elite Dangerous. But that wasn't actually the problem that I thought was interesting. The problem is that if 8 light years is indeed the infection range, 90% of stars in our galaxy have another star within 8 light years. It's...
Oh, I get what infection means in this context. Basically, it means how far you can go.
50714, which was infected by Sirius, which was infected by Epsilon Eridani. They also say that WISE infected Wolf 359, the Land 21185, and Ross 128. From this, they deduced that...
it's a contagious disease. But instead of, like the common cold, it's between stars. What the fuck?
That the range at which astrophage can survive interstellar distances is 8 light years, and thus the range that it can infect other stars is 8 light years. Problem is, in real life, WISE is 11 light years from Sirius, so that's a no-go. The shortest distance from Tau Ceti to Sol in less than 8 light-year hops would have been Tau Ceti to LaSalle 9352, LaSalle 8760, Ross 154, the star within 8 light years. It's, in my opinion, probable that astrophage would have spread throughout the entire galaxy like a plague, infecting nearly every star. It sort of depends on the distribution of stars, and there are some filters that could have limited it, but I just thought it was interesting to visualize what an 8 light-year range spread would have looked like in our nearby stars. This is using the ATHYG stellar catalog, by the way, which is not a full representation of all the stars in our neighborhood, but it's pretty close. The point is, this is an awesome sci-fi. I saw an interview with the directors of the movie who said that the story is about saving the galaxy by making a friend. But the novel is deeper than that. It's about making a friend who's a complementary thinker to you, who's not the same but gets you and you get him. And it makes me feel less alone, I guess. Although he did have to go to another star system and find a literal alien to feel less alone. But having seen the movie and seen reactions from all different types of people, it's starting to illustrate to me the difference between me and the normies. It's starting to. I still need some time to process it. But
we'll pay a sponsor.
If you want to dig even deeper into the math and science behind Project Hail Mary, I would recommend Brilliant. Brilliant is like the teacher I wish I had. I never did. I don't learn by reading textbooks. I learn by doing it myself, which is exactly what Brilliant teaches you via interactive problem solving in a host of fields you'd need to science your way out of interstellar problems. They have courses in math, science, coding, and AI, all crafted by world-class teachers from MIT, Harvard, and Stanford. They have a course on exponential functions, which is one of the core concepts underlying this time dilation and astrophage infection rates. but there are a ton of other interesting topics for kids and adults. They're designed for ages from 10 to 110. You can learn for free on Brilliant for a full 30 days by going to my link, brilliant.org/the overview effect. Scan the QR code on screen or click the link in the description. And Brilliant has also given my viewers 20% off an annual premium subscription, which gives you unlimited access to everything on Brilliant. I'm extremely selective with what I choose to promote on this channel. I say no to almost everything. Brilliant is one of the few that I cannot recommend enough. Thank you, Brilliant.
One of the better videos I've seen. But lately I've been seeing some low quality stuff. Freaking do not recommend on a lot of stuff. I like this video.